fuzzy logic and fuzzy mathematics. So I am trying to introduce Professor Chakraborty. So Professor Chakraborty is a retired professor from Department of Pure Mathematics, University of Calcutta, and he visited different prestigious institutions like School of Cognitive Science, Jadavpur University, adjunct professor at IIIT Delhi, visiting professor, Indian Institute of Engineering Science and Technology, Shibpur, visiting professor of Indian Statistical Institute, Calcutta, and also visited as a guest professor in Changqiu Southwest University, China. Also, he has visited as a guest professor the ISAR Kolkata, and his research area are non-standard logic, fuzzy set theory and fuzzy logic, rough set theory and logics of rough sets, para-consistent logics, foundation of mathematics, mathematics and culture, logic of diagrams, functional analysis, topology, knowledge representation. So he has also published more than 250 papers in reputed journals and 100 conference presentations. He also published 7 books by Springer and from your in Bengali language also. He also edited one book published from Springer in 2 volumes, Handbook of Logical Thought in India, and also he edited 5 conference proceedings published by Springer. Professor Chakraborty has collaborated with different persons in different countries like Germany, Poland, France, Australia, Italy, Canada, France, your China, your Hungary, Greece, etc. He also awarded or honored by that fellowship Germany, fellow of IIAS, Indian Institute of Advanced Studies, Shimla, fellow of West Bengal Academy of Science and Technology. He also fellow of ICPR, Indian Council of Philosophical Research, fellow of International Rough Set Theory, and life member of Calcutta Mathematical Society and others. He has guided 15 PhD scholars, and he has organized more than 50 conferences, seminar, workshop. So with these few words, I request Professor Chakraborty to deliver his lecture. So we are very grateful for your presence and accepting our invitations.
Thank you very much. Please, somebody should help me in.
Yes, yes, yes.
Yeah, okay. Um, oh, let let the slides appear. Meanwhile, I thank Sridharacharya Academy of Mathematical Sciences for organizing this conference and inviting me to give a talk, particularly to Professor Madhumangal Paul, who is well known to me for many, many years. Uh, this is the 60th anniversary of fuzzy logic. I met Professor Zadeh 3 times. First time in France, second time in India, Kolkata ISI, and third time in Poland, Warsaw. Do you hear me now, Madhumangal? Is it okay? Do
Yes,
you
sir,
hear
it's
me?
fine.
Am I audible? Huh?
Audible, sir.
Oh, okay, fine. Um, I should also mention that we in 1984 the first All India conference on fuzzy set theory was really organized by the University of Calcutta, our department, and where one major personality was Professor D.J. Dr. Majumdar of ISI. Professor Dr. Majumdar was really, in that sense, the pioneer of fuzzy set theory activities in India. But basically, he was a uh, application person in Kolkata University. we started work from the theoretical side. And so together, also Dr. Mazindar's group in ISI and our group in Kolkata, together, we set up something and called ISFAME, Indian Society for Fuzzy Mathematics and Information Processing, which contributed a little bit in the development of fuzzy set theory in India. And as I mentioned during my last, intervention during the last talk, that the first um, PhD thesis, full PhD thesis in fuzzy set theory was by Nili Dash, who worked with me um, in the area of fuzzy relations. But his particular significance is that, but it is not fuzzy relation on ordinary sets, but it is fuzzy relation on fuzzy sets. And um, what they was mentioned in the last talk, that there are vertices with with weights and also weights at the edges, and there was an interesting relationship that the weight at the edge should be less equal to the minimum of the weights of the vertices. So we that time, I mean, in 80s, we really did that, and we had reasons, theoretical reasons for doing that, not practical reasons. So I would request um, you, if if you can find um, somehow those papers, some of those papers, it will be quite nice. Uh, Today, my talk will be on fuzzy logic, really. So, as you see, the title is Graded Consequence Relation and Fuzzy Logic. Uh, so, uh, next slide, please. Please pass on. Yeah. So, what we mean by logic is that it is logic consists of language and a notion of consequence. Language means formal language. Uh, so the next is that the consequence is defined, by consequence, we mean premise, from premise, some conclusion follows. This relationship between premise and conclusion is called consequence. Now, consequence is defined in, I mean, classically in two ways. One is the operator approach, and the other is the relation approach. Next slide, please. Uh, in the operator approach, you see, it is an operator. It is a function C, which is from the power set of the set of sentences F, or set of formulae F, to the set of formulae. So, sorry, to the power set of formulae. So it is a mapping from PF to PF, satisfying these conditions. You can see the topological uh, um, what should I say, topological flavor of the consequence operator. The first one is, so you can think of C as a closure operator, and you see the um, first three, and then the fourth one is the compactness. Here is a typo. This y should be is not only a subset of x, but y is a finite subset of x. So Cx is the union of all Cy's, where y's are finite subset of x. I am trying to present what was there in the classical logic, and we will finally generalize those things in the um, fuzzy case. Okay, next slide, please. Next slide, please. Yeah. Yes. Now this is the consequence relation. The first one is consequence operator, and you have now a relation. It is a relation. I mean, classically, it is a crisp binary relation between the power set and the original set of formulae. So X, Y, Z, etc. here, these are sets of formulae, and alpha, beta, etc. are single formulae. So the first one says that if alpha is in the premise X, then alpha should follow from X. The second one says that if alpha follows from X, then alpha also follows from any any superset of X. And the third one is very interesting. It is a generalized version of transitivity relation. It says that if beta follows from X for all beta belonging to Z, and if from X union Z alpha follows, then alpha also follows from X. Technically, it is called condition COT, but it is actually generalized transitivity relation. Well, so this was given originally by Gensen long back, uh, and mm, and see the last one. It says that if alpha follows from X, then alpha follows from some finite subset of X. Okay, next please. Now, there is so all these you see, this is very formal. Now, let us come to the semantic part of it, so meaning part of it. So, so this is also a consequence relation, but this is normally defined, written as a double turnstile. This we read as double turnstile. So there are two ways. One is truth value semantics, and the other one is algebraic semantics. This next. So let's see what truth value semantics says. This is the standard understanding of this. It says that if the premises are true, then the conclusion has to be true. If X is all elements of X are true, then alpha should also be true. Mm, mm, just a moment, please. Uh, then alpha should also be true. This actually takes the following form. You see the last one, the last sentence, the last line. Uh, uh, you see, oh, 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 um, I mean, when I say X is true, the premises are true, that means actually we are making some kind of valuation. I am giving values depending on situations. I am giving some values to the formulae belonging to X. So those valuations, I mean, those values or those valuations which make all the elements of X true, that means which gives the value 1, which assigns the value 1 to all the sentences of X, is really, in a sense, the mathematically speaking, the mm, what is called, it is a um, um, the when the set is defined by the by the function. Um, what is the name? Um, it is the. I'm sorry, I forgot. It's the standard understanding. So make all the when you define a set, you define it by a function where the values of the members of the set are 1 and the values of the other non-members of the set are 0. So um, this same thing is T. And so you see the last line, this is really the form of the um, the truth value semantics. It says that alpha follows from X if and only if when every member of X is a subset of T, it implies alpha is also a member of T. Come to the next one, please. And here in the algebraic semantics, what happens? You take the conjunction. you take ANDing of all the members of X. So alpha 1 and alpha 2 and alpha 3 and alpha n. Suppose there are n members in X, take its valuation. So that valuation should be less equal to the value of alpha, the value of the conclusion. So this is the algebraic way of taking this. The value set L, sorry, the value set L is an algebraic structure which has, which has uh, um, some properties. I will come to those properties later, because this L has to be actually extended. In this case, in the classical case, L has only two values, 1 and 0. 1 for true and 0 for L. That means it becomes a Boolean algebra. Okay, come to next one, please. So consequence, on the left you have consequence in the syntactic way, and um, consequence double turnstile. This is the meaning part. So here you have language, and there you have meaning, you have formulae, you have sentences, axioms. There will be axioms in the syntactic part. There will be tautologies in the semantic part, and there will be rules in the syntactic part, corresponding valid rules in semantic part, and there will be derivations. Derivations means coming to some conclusion from the axioms by using rules. And similarly, here we will also have derivations, but you will get validity. So on the left, you have proving. So you prove the consequence from the actions. On the right, you you establish the validity, and when it comes to validity, either it has the truth semantics or you have the algebraic semantics. Next, next, please. Okay, so in case of classical two-word logic, the two semantics becomes equivalent. That's the nice part of classical logic. That means when x follows from alpha follows from x, uh, or alpha is a consequence of x, if and only if alpha is a consequence of x in the semantic way. On the left, on the left side, on the first part, you derive alpha from x purely uh, manipulating the symbols. On the right, you enter into the meaning. You say when the premises are true, the conclusion has to be true. So these two are two different concepts of um, consequence. One is called syntactic consequence, the other is called semantic consequence. But in case of classical logic, classical two-word logic, in which we do our generally our entire mathematics, is the two coincide. Next, please. Uh, yeah. Um, Now, the consequence, uh, this is the main point of graded consequence. Consequence is a meta-linguistic notion, and hence the defining sentence of the consequence involves meta-linguistic connectives. You see, in this, you see this particular meta-linguistic sentence, what it says. It says that from X, semantically follows alpha. This is horseshoe. Horseshoe is if then. So it is implication. So alpha implies beta. This formula follows from the premise X semantically, double turnstile. What does it mean? It means that if all the any valuation in which, or any situation in which all the elements of the premise X are true, then alpha arrow beta is also true. Alpha horseshoe beta, that means if alpha then beta is also true. Here you see there are two kinds of implication involved. One, you see the horseshoe, and the other one is the arrow. Arrow is the metalinguistic implication. On the other hand, horseshoe is the object language implication. I will come to what is meant by object language and meta language more properly in perhaps next slide. So, but the main important issue in in graded consequence theory is that the distinction of level should be mentioned. One is the zero level, the formula level, the object language level, where you have this horseshoe as the implication. In the meta level, you have the implication arrow. Sorry, arrow is as the implication. Okay, please, next one. Here is a list. In this list, you see the what are there in the object level. This is called level 0. You have the formulae, that means the sentences. You have the sets of formulae, X, Y, Z, etc. And you have finite sequences also of formulae. All these we put in the object level. That means the level 0. What are in the meta level? In the meta level, things are like this. Suppose the first is alpha is a syntactic consequence of X. So alpha is a formula which we put in quote is a syntactic consequence. That means it is a relation of, I mean, relation related to X. X we also put in quote. Similarly, if you take semantic consequence, this also comes to the meta level. And suppose X is inconsistent or X is consistent. Now, these terms, syntactic consequence, semantic consequence, inconsistency, consistency, etc., all these are about the object level entities. So, if something is about the object level entities, that comes to the meta level, that comes to level 1. Now, you may have to speak something about the meta level entities also. For example, the last example is this. So here you say one is the meta level entity, that is alpha is a consequence of X, and the other is again a meta level entity, which is X union negation alpha is inconsistent. Now, at the next level, that is meta level 2, you are saying that if the first level 1 entity is true, then the second level 1 entity is also true. So that this is really something which is very deep philosophically as well as technically. And when I say technically, it means I have in mind Alonzo Church's, the lambda calculus like thing, where which is really the basis, in a sense, the basis in computers. I mean, in the computer language, you always use these levels. Okay, next one, please. Now, the importance of distinguishing levels from the algebraic standpoint, from the philosophical standpoint, there is something called use and meaning. Using and meaning, you see the next example. When I say this cat is strictly vegetarian. Now, here, the word cat is in the object language. Here is an object language set. This cat is strictly vegetarian. Uh, but the same word cat can be used in the uh, I mean uh, in another way. When we say the word cat, for that we put a uh, a quotation mark. So now cat with quotation is an English word. So it is something spoken about the word cat. It is not an, although here it is also an English sentence, but uh, we can in general make it as a Bengali sentence like cat একটি বাংলা একটি ইংরেজি শব্দ. I could write like that. Quote unquote cat, একটি বাংলা শব্দ. Sorry for my use of Bengali language, but I think that will make clear many of here definitely are Bengali, but I hope my idea goes to all of you. Okay, next please. Next please. Here I skip. I want to skip this because this is an example from the logic where the object, I mean, to make distinction between the object language sentences and meta language sentences. Okay, please. Next one. Now, semantic consequence generalized by Shoesmith and Smiley. Okay, I will just say one word on this. It is that when in the semantic consequence, you might have remembered that we took all possible valuations, all possible TIs, which make X true also makes alpha true. That is the understanding of logic, validity of consequence relation. But instead of taking uh, all possible situations or all possible valuations, we can definitely take uh, some, not all, because all is very problematic term. It all you may not require in a particular context. In a particular context, you may require some situations. For so for use, definitely you only consider some situations. So technically, instead of taking all valuations, all functions, if you take a set of functions, TIs, then you write this whole thing, I mean, which I have written before in terms of this collection TI. So it is a semantic consequence relation in terms of the valuations BI. So you have the valuations TIs, and with respect to TI, you define a semantic consequence relation, double turnstile TI in this way. Please, next one. Uh, Now here is the trump card. So what happens if you define in this way, semantic consequence relation? So it says that if you have a consequence relation single turnstile, which is defined axiomatically as before, I mean, you might remember Gensenian conditions. So if you have a syntactic consequence relation, then there exists a collection, these are functions, then there exists a collection TIs for with respect to which you can define semantic consequence relation double turnstile TI and these two coincides, like the classical case, these two coincides. Okay, but there is a converse also. You take the uh, uh, you take a collection of TIs and you define the double turnstile relation, it turns out to be a consequence relation syntactically. I mean, it will satisfy the four axioms, the three axioms at least, first three axioms of this. So once you get the representation theorem, you become happy uh, in mathematics, definitely, but also I think from the standpoint of applications. Next one, please. No, okay. The another important meta-linguistic notion is consistency. So the consistency is defined. We say that a set of premises, a set of sentences is consistent. So what does it mean? Syntactically, it means that either syntactic one or syntactic two. Generally, we mean syntactic 2, which says that some alpha, some formula, or some sentence alpha and its negation alpha, both follow from X. If this thing happens, then we say that X is inconsistent. So, mm, mm, um, okay. So what I have written consistency in the mm, uh, in the title, but one and two really mean inconsistencies. So you can see syntactic two really shows that X is inconsistent. and its equivalent is syntactic one, equivalent in classical sense, in syntactic one, where everything follows. It is called explosion property. If X is inconsistent in the second sense, then everything follows from X, uh, and and vice versa, obviously. So, so syntactic one and syntactic two are definitions of inconsistent set. So when will be X consistent? When that means when these things do not happen. So not everything follows from X, not there is no formula alpha such that alpha and negation alpha both follow from X. In that case, this X is called consistent. Semantically, X is consistent. You all know as mathematician that when we say that X as a model, it happens that when we introduce some axioms for some concept, immediately after that, we need an example. The example is the model. So when when we need that the axioms, for example, say topology axioms, for example, say metric axioms or Boolean algebra axioms, are they consistent? Or is it, what is the guarantee that no formula, no sentence and its negation will follow from this? How do you know beforehand that it is consistent? The method, one method is that it has a model. That means it has an example. Okay, please, next one. Uh, now, in the language, obviously, we have already assumed negation in the objective language, object language, because that negation, when I put a curl sign before alpha, it means I am taken, um, I have taken negation. So, what does it mean? Does it mean that there may be languages where negation is not there? Yes, it is possible to develop languages where negation is not required. But I skip that. Okay. Next one, please. Next one, please. Um, uh, I think short of time, these are some generalizations. I skip this Surma's equivalence. What he says is that there is a kind of coming and going between the axioms of consistency and the axioms of consequence. So if I have a set of consequence, I have a consequence relation defined by axioms, and then I can pass on to the consequency axioms, consistency axioms, and vice versa. These actually we'll be using after generalization. Okay, please, next one. Uh, so this is the inconsistent axiom. The first one is consistency axioms, and the when you say actually we'll be using inconsistency axioms in our work, in our generalization work. So we had to write inconsistency axioms from the consistency axioms. Okay, this next one. Equivalence between consequence. This is what I have already mentioned, how to pass on, how to go from the consequence to the consistency, from consistency to consequence. Okay, please. Next one. Uh, in our case, in the graded consequence case, we have made two kinds of generalization. One is we have adapted Smith and Smiley, and we have adapted many valued logics, obviously, for fuzzy case. Smith and Smiley, I have already mentioned, where instead of all valuations or all truth valuations, or some TIs, truth valuations are taken, and many valued logic, I'll come to that. Okay. So we'll make two things for generalization. One is that will come down to some truth values Ti instead of all truth values Ti. There's one. And second is we'll use, instead of only values 0 and 1 as the truth value, we will be using um, any number between 0 and 1, or more generally, a a value from the lattice on special kind of algebra. Please, next one. Uh, I skip this. Please let us go. Here, I wanted to make a case for many valued logic. Let us skip. Let's go straight to the next one. Next one, please. Uh, well, uh, many valued logic was already there right from 1920s onwards, but uh, in formally were considered. I mean, it was more mathematical. Formally, where instead of having truth values, 1 and 0, uh, people started assigning more than two truth values. But after Zadeh, 1965, we had an actual scenario, actual sentences where really we needed uh, uh, more than uh, more than two truth values. So that is a very much, I mean, I should say, turning point. So it is Zadeh. Zadeh used basically 01, and Gauguin's this very seminal work just almost after that, after 65, where instead of 01, he um, used lattice. Okay, please, next one. Next one, please. This you can understand. This is the pictorial representation of classical logic, classical case, where you have uh, P and not P very crisply, and in fuzzy logic, you have P. From P, you gradually pass on to non-P. Okay. Mm. Okay, please, next one. Fuzzy logic as found in the existing literature. Okay, please go on to the next page. There are two ways in which fuzzy logic is used. One is the way is called fuzzy logic in the wide sense, and fuzzy logic in the narrow sense. In the wide sense, wherever fuzzy set theory is used, we say, sometimes we say that fuzzy logic has been used. Uh, this is very loose way of using the word fuzzy logic. But as you have seen, logic is a special branch of study where you need to have this consequence relation properly defined, etc., etc. Uh, if we try to introduce fuzzy logic in that sense, in that way, and then it is called fuzzy logic in the narrow sense. Now, there are some names here: Gauguin, Pavelka, Novak, Wortwald, Hole, Bodo, Esteva, Jerla. It is a mistake here. Jerla, Hayek. They are, they have introduced, they have done work in fuzzy logic in the narrow sense, and later they called it mathematical fuzzy logic. And fuzzy, there was something called Zadeh's fuzzy logic, which Zadeh, of course, basically used fuzzy sets. But at one point of time, he also went for fuzzy logic, in his own way. Please, next one. This is Zadeh's, it is well known. Uh, uh, if x is p, then y is q, x is p dashed. It is not exactly p, so it is something closer to p. Then what will be y? Now, Zadeh gave this kind of um, calculation for what is y, what should be y. So P is a fuzzy set, so it's a mapping. Q is also a mapping. P dash is also a mapping. So computing P, Q, and P dash in this way, he arrived at a value which will be Q dash, and he concluded that given the two premises, y is q dash, y should be q dash. This was how Zadeh first is the first person very uh, very, very, uh, what should I say? We could see the future. And okay, next, please.
So, sir, can I request you to
Yes,
finish
I'm
to finish within 5 minutes?
okay. I'll come to I will come to the definition and
Okay,
stop.
okay, sir. Okay, sir.
So now this is Gauguin's position. You see what he says, that if P is true at least to extent A and P implies Q true at least to extent B, then Q is true at least to extent A dot B. This dot Gauguin used as the T norm, as the product norm. Okay. Next one, please. This was Pavelka's. Actually, what we'll do, we will we'll depart from here. Uh, Go next one. Next one, Hayek's position. Hayek has become a very hot uh, name after his seminal work, book also of fuzzy logic. And what he did was more or less what Gauguin did, but in a very, very uh, um, formal way. So you see here, uh, um, you see here, I mean below, P is true at least to extent A, P implies Q is at least true at least to extent and B. Then Q should be true at least to extent something. This something can be product, can be NET norm, can be something else. Okay, next one, please. Okay, it's the same. Please pass on to next one. Next one. Uh, Please drop this, drop this. Yeah, here, what we did is this. Go to next slide. Next slide, please. Next slide, please. Next slide, please. Uh, Next slide, please. Next slide, please. Next, please. Next. Here, you see those three conditions are now generalized here. Instead of this, the main issue that the consequence relation is now a fuzzy relation. So there it is a fuzzy relation between the premise set X and the conclusion alpha. X is a set of sentences or formulae. Alpha is a single formula. X curly turnstile alpha is a fuzzy relation. And the way we have written it is grade, GR, grade of alpha fuzzily implies X fuzzily implies alpha. This whole thing is denoted by, okay, 1 or something else. So the value of grade of X curly turnstiles alpha is now a value of between 0 and 1. The three conditions that I mentioned before are now these three conditions, 1, 2, and 3. You can see the changes. You can perhaps see the changes. So this is how the axioms of consequence relation were generalized in the fuzzy case. Okay, next one, please. Uh, Again, semantically, this whole thing was taken in this way. You might remember the formula for semantic consequence. And here we have this formula for graded semantic consequence. Okay, come to next one. Okay, so this is the just calculation. So ultimately it comes to sigma dash. So the sigma dash is the expression for the semantic consequence with respect to the set of values ti. Okay, graded semantic consequence. Okay, now next one, please. Uh, Again, we have these representation theorems as we got in case of classical case. The first one says if I have a graded consequence relation, style alpha, early turnstile alpha. Then there exists a collection. These are fuzzy sets now. Yeah. In the previous case, they were ordinary sets. Ti of fuzzy subsets of formulae such that the semantic consequence obtained in terms of Ti's is the same as the syntactic consequence in terms of yeah, graded syntactic consequence. And conversely, so the first gives one direction and the second gives the other direction. So this is again how the we uh, have established the relationship between the two, and we become happy. I would ask you to come to the jump to the last but one slide. Is can you is possible? Which summarizes. Okay, next one, next one. These are examples, some examples. Okay. So I skip this because now we have generalized the inconsistency relation. Okay, okay. Uh, Next, please. Next, please. Next, please. Next, 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 next. Okay, summary. Come here, come here. Okay, summary. So the features of graded consequence relations are the following. This is important from, I think, should be important from the standpoint of application. It is local in the sense that the logic emerges out of a context given by a set of valuations Ti. Uh, this is first. The set Ti may be interpreted in many ways. First, as truth values. Second, as opinions of experts. Three, as beliefs of agents. Four, as situations or words. Now, syntactic part is also quite well defined, is already there. We have shown it is weighted, and what the syntactic consequence relation will mean. I mean, what will the value will mean. It may be interpreted as the strength of the rule. Next one, next page, please. The degree of a rule is the extent to which the conclusion of the rule follows from the premises of the rule, taking TIs into consideration. Hence, syntactic derivation is graded. The grade may be interpreted as the strength of derivability. Next, so semantics is that is context plays one of the main roles in proposing a logic with graded notion of consequence. Soundness, completeness, etc. comes there. I think that this is the advantage. I mean, from the standpoint of um, application, uh, which may be used by those who want, okay, who want to apply the theory. Okay, come to the final slide. Maybe uh, these are the references. Next, please. Next. Now there's a picture of a book written by us. Yeah. So we did, Shoma actually did her PhD with me in graded consequence. There was another PhD in graded consequence. Now, we wrote a book in 1917. So you can see the title, it is Theory of Graded Consequence, a general framework for logic of uncertainty. So I have not worked anymore, but I hope that um, for actual applications, graded consequence can be mm, used. Uh, it can be used in a better way than mm, has been used by the um, by the theory of fuzzy logic in the strict sense. Okay, thank you very much.
Thank you, sir,
Thank you
for
very
your
much.
nice and informative lectures. So, if there is any question from the audience, so you can ask any question. This is a very fundamental
Grading.
works on logic as well as fuzzy logic.
I think it was a bit hasty, and maybe had it been, you know, if I could present it physically, it would have been better. Um, okay, thank you.
Since
Then,
there is no question, so we uh, thanks to the speaker, Professor Kumar Chakraborty, and from our society, Siddhar Acharya Academy of Mathematical Sciences is honored and pleased to present a Lifetime Achievement Award to the great scientist and mathematician, Professor Mihir Chakraborty. So I'm showing the certificate. This is the certificate, sir.
thank
So
you
I
very much.
request
Thank
you
you
to
very
accept
much.
our
I feel honored.
Achievement Award
Okay, I feel honored. Thank you. Thank
for
you.
your great work of studying
Thank
logic
you
as
very
well
much.
as
Thank you
mathematics.
very much.
Thank you, sir.
Congratulations, sir. Congratulations.
হুম, কি বলছো? কিছু বলছো বাংলায়? Okay, all right.
Okay, thank you, sir. Professor Chakraborty and Professor Pal both. So our last lecture before the lunch will be delivered by Professor Mohanmangal Pal himself, and this